Welcome back for this third example. In this video, we're going to go over the predictive maintenance example that you explored in class. As always, we'll focus on learning how to perform a survival analysis in R in order to obtain the same results showed to you during the lectures, and most importantly, for you to be able to perform your own survival analysis on your own datasets. Bear in mind that our issue in this example is to estimate the remaining lifetime of our pieces so we can better organize our maintenance efforts. Alright, let's get started. We set our working directory to the folder where we have downloaded the predictive maintenance dataset, and we then run this line in order to clean up the memory of our current R session. We're now ready to load our maintenance dataset and call it data, and we load it using the read.table function using the sep argument and the header argument. Now let's get familiar with our data by calling the str function. And we find out that we have 1,000 observations in this dataset and 7 variables, namely the lifetime variable, which reports in weeks how long it has been used until now. Then the broken variable, which takes the value 1 if the piece is broken and 0 otherwise. Then the pressure index, the moisture index, the temperature index, the team that is in charge of maintenance, and the provider that supplied the piece. Let's now check out some summary stats on our dataset to understand the order of magnitude of our variable and gain better intuition of our data. First thing that is of interest is the proportion of the pieces of observations that are broken. And we see that we have 0.397, so about 40% of the pieces in this dataset are broken. And then we may be interested to know that the mean pressure is 98.6, mean moisture index is 99.38, and mean temperature index is 100.63. The last thing that may be of interest is to look at the breakdown of pieces maintenance allocation to teams. 336 pieces are allocated to Team 1, 356 to Team B, and 308 to Team C. One thing that we've done before in order to predict the value of a numerical variable is to build a linear regression model. So let's try it out here. Let's call our model linreg model, and we use the lm function. Our dependent variable is lifetime, and then the dot indicates that we use all the other variables, and then the minus broken indicates that we use all the other variables minus the broken variable. But we could add all those variables to the model after the tilde and separate each of them by a plus sign. But again, it's just more efficient, and I want you to know that you can do that if you want to. And then we set data equal to data to use our dataset. Let's run the line. Now let's check out the output of our model. What we see is that it looks like the fact that Team C was in charge of the maintenance of the piece is statistically significant, as well as the fact that the piece was provided by provider number 3. And both of them seem to impact negatively on the lifetime if we look at the coefficient and its sign. But as was explained in the lecture, using the output of a linear regression in this case is inaccurate. In this case, we cannot rely on the output of the linear regression model for a very simple reason. For 60% of the observations, those are not broken. The lifetime is not the lifetime until the piece was broken, but rather the lifetime until now. So the truth is, we don't really know what the final value of lifetime will be for pieces that are not broken yet. All we know is that they're still working until now. As Professor Glady explained in the lecture, this is a right-centered problem that we will tackle in this video by using a survival model. In order to create such a model in R, we need to install the survival package. And in order to do so, we need to use the install.packages function, open parenthesis, and survival in quotes. We run the line and it may take a few seconds. Now we need to load the survival package by using the library function, open parenthesis and survival, without quotes this time. We run it and the package is loaded. Now please note that while you will not have to reinstall the survival package for your subsequent analysis, you will need to load the package every time you start a new R session. In any case, we're not ready to start our survival analysis. Our first step is to set our dependent variables. In R, we can do that by using the serve function, and in this case, we want to provide the lifetime, and whether or not the piece is broken. And we call the output dependent vars. We're now ready to build our model that we will call servReg. To do so, we use the servReg function. We input our dependent vars, which is the output of the previous line, tilde, and then our independent variable, namely pressure index, moisture, temperature index, team provider. We then set the dist argument equal to Gaussian in quotes because we want distances to be computed using the Gaussian method. And as usual, we say data equal to data, which is our data set. We then run the line. At this point, we should assess our model on out-of-sample data, for example. We won't do it here because we checked it for you, but keep in mind that you should not use a model without being confident that it does well, or at least without knowing its limits. Let's now check the output of the model. As we always do, let's check out the p-value to see which variables are statistically significant. We see that first, the moisture index is statistically significant. The temperature index as well, if the piece was maintained by team C, and if the piece was provided 2, 3, or 4 are all statistically significant. Now, to assess whether the effect is positive or negative on the expected lifetime, we look at the sign of the coefficient. For moisture index, it's positive. For temperature index, it's negative. For team C, it's negative. For provider 2, it's positive, and for provider 3, it's negative, and provider 4, it's positive. When I say positive or negative, it is on the expected lifetime that I'm talking about. So we see that if the team was supplied by provider 2 or provider 4, the expected lifetime is positively impacted. But in any case, it is information that is worth knowing and that is worth investigating. Now that we have a working model, let's go back to our initial problem, which was to estimate the remaining lifetime of our pieces, which are not currently broken. To do so, we're going to make predictions using the predict function, which will output the expected median time to death of each individual element. Our first argument is the model that we just built and that we're going to use to do our predictions. Our new data argument is set equal to data, which is our data set, and we set the type argument equal to quantile in quotes and p, or percentile, equal to 0.5 in order to get the expected median time to death. And we store the output in eBrec. Now, to make an interesting report, we can organize the output of eBrec in a data frame with the data frame function, and we call the output forecast. We can then add a column with the lifetime for each observation by typing forecast $lifetime equal data $lifetime, and then a column indicating whether or not the piece is currently broken with forecast $broken equal data $broken, and a last column which we will call remaining LT for remaining lifetime, which computes the remaining lifetime by subtracting the lifetime variable from the original dataset to eBrec, which is the output of our predict function. Let's check out the output by typing view. Now the output is interesting, but we see that we still have the pieces that are broken and that we're not really interested in since it's too late to do some maintenance on those. And the other thing is that our output is currently not prioritized. We don't have the pieces that will be broken shortly that we should focus on. What can we do to improve the output? First, we can reorder our forecast data frame and order it by increasing remaining lifetime by using the order function. And from forecast, we can select only the pieces that are not broken yet, that is those for which the broken variable is equal to 0. Now let's check out the output of actions priority, which is our final dataset. That's much better. We can now allocate our maintenance staff to the pieces most likely to break soon and maybe avoid some breakdown timeout. So that's it for the third example. I will see you in the next video.